I guess I'll get started. Otherwise, we'll run out of time. I'm already 30 minutes short. So I will be quick in the explanations and in the Q&A. If you have any questions, I will go ahead, Hayden.
Pedro, hang on for just a second. James, did you need a second to the recording's ready?
No, sorry, everything is set up. Pedro, go ahead, but if you run over by
I
a
think
few minutes, it's okay.
Okay.
Yeah.
So let's remember, everyone, that my name is Pedro dal Castel, and this is my final lecture of today. It's a guided exercise, the Avascular Tumor, that summarizes everything we've learned so far in terms of Python coding and setting up secretion and uptake in the simulation. So let's get started. Remember that this is being recorded, live streamed, and distributed. I'll go over some biological background. This is the avascular tumor in a petri dish. In the center, the cells are dead, so we call it a necrotic core. And there is a middle layer zone where the cells are barely surviving. We call it quiescent zone. And these cells in the quiescent zone, they are unable to proliferate. They lack the necessary resources to proliferate, which is a very demanding activity in terms of energy. And in the outer layer, we have the proliferating zone. And why is that so? Because, sorry. So here you can see the tumor growing, and as it grows, the inner cells start dying. There are some questions we can consider when building this model. For example, how much time does the avascular tumor spheroid requires to grow? And how does it differ from in vitro to in vivo? Avascular, so vascular or vascularity, it means blood vessels. Avascular means that the tumor lacks blood vessels or capillaries in it. The vascularized tumor is when the tumor gets access to your blood vessels, hence boosting its access to nutrients. And why there is a necrotic core? Well, because nutrients have to diffuse in the tumor, and only the outer layer will have better access to nutrients. As the nutrient diffuses through the tumor, it gets consumed, it decays spatially, and as we've covered 3 lectures ago, there is something called the diffusion length, and the diffusion length, it's what ultimately regulates the size of the outer layer of healthy proliferating cells. So this is my paint diagram. We have an outer healthy proliferating cell, an intermediate quiescent layer, and an inner necrotic layer. I promise that for next workshop, I will come with better diagrams. And cells have to transition between states depending on whether they access more or less nutrients. So if they are proliferating and their nutrients get scarce, they transition to the quiescent state. And if it gets more and more scarcer, they should transition irreversibly to death, to necrotic. And transition from healthy proliferating to quiescent is reversible. So if a quiescent cell gets access to more nutrient, it can reverse its phenotype to proliferating and starts proliferating again. There are different boundary conditions we can set up. For example, we can use the boundaries to simulate blood vessels. So it's still avascular because the blood vessels are outside the tumor. They are not inside the tumor. So you will have a necrotic core no matter what. So you can use, for example, the discussed in class constant concentration boundary condition. You can also set up a constant flux of nutrient in the tumor. And the one we'll use is medium will hold the field at a constant value. This is the this is how we will model the supply of nutrient. As if, so this is the same as saying the tissue around the tumor is highly vascularized and nutrient in that area is immediately replenished. So the tumor time scale, the time scale for tumor growth is extremely slow in comparison to nutrient replenishment in the tumor, in the regions around the tumor, sorry. So this is the exercise. You don't need instructions because at this point you are able to set a simulation up and you're able to change the parameters, or at least that's the idea by now. So if you have any difficulty, please feel free to ask us in the chat, and TAs and I will be able to help you. So go ahead and set up a simulation following these settings. I will give you guys 5 minutes, and then I will do it myself. Yes, you need, so let me see, apparently, if I'm not mistaken, when you select mitosis, it automatically selects volume local flex. But to make sure, as Yasmina suggested, oh yeah, that's, yeah, no, you don't need to set growth. No, you just need mitosis and volume local flex. That's all you need. Yeah. For a moment, I thought I made a mistake, but no, that's fine. Yeah, we'll go through the next steps in a minute. Okay, so I'll go ahead and build the simulation myself. So I put this to the side and open to edit. All right, so if you're having difficulties, please look at me doing it. So I'll go new CC3D project. I will go on vascular tumor. Then here, blob initializer, copy range 2, 256 by 256. Okay. Now,
Pedro, why don't you start over and go slower with that and explain why you're doing the things you're doing? Because I think people are tired, so that they can't type quite so fast. Or you could do it twice, either way.
Okay. So
And I think you neglected the periodic boundaries the first time.
oh, true. That's correct. Yeah. All right. So let me go slower here. I put a name in the simulation. Then I set the lattice dimensions to 256 by 256 in the X and Y. Now, periodic boundary condition on X and Y only. Don't change in Z. Z has to remain non-flux. Then I changed the pixel copy range to 2. That's right here. And I select blob as the initial cell layout. Now I'll go next. And here I need to set the 3 cell types. Prolif for proliferating, Quies for quiescent, and necro for necrotic. These are the 3 cell types we need, as we need to build the tumor spheroid with the 2 phenotypes and cell death. So I type the name of the cell type and press enter. Then I do the same for quies and the same for necro. Next, we'll create the field nutr for nutrient and press enter. So you should see in the table field name and UTR and solver diffusion solver FE. Next, here I need contact, so check contact. I need secretion, so check secretion. I need mitosis, so check mitosis. And finally, volume local flex. Check that. Next. So here in the secretion plugin, you probably stopped here if you're following the instructions. So here there is an easy way to set the medium to secrete, because this is a tricky one. So we'll use this little window here to do that. So what we do here is select the field nutr, the cell type medium, that's the default. So that's right, that's okay. And then we select constant concentration. So I checked this option here called constant concentration. It was originally in uniform. What we really want is the constant concentration. So again, in the secretion plugin window, the field is nutr, cell type is medium, and then you check constant concentration. That's all I did so far. In constant concentration, in this field, in this blank field here, we set this constant concentration to be 100. And
Can this
then,
value be
sorry.
modified in XML?
Yes.
Okay.
So did you already set your simulation up and you need to change it, or you are here with me?
Yeah. Yeah.
Okay, I'll go over it, no worries.
I'm looking for it. I'm not
So,
finding
um, Now I go and hit add entry. So what I'm seeing here is nutr medium 100 and type constant secretion. Let's see how you guys are in terms of exercise relaunch. If you skipped the secretion plugin, that's okay. All right, we have a good completion sample. So if you need help, please ask for TA's assistance. Now I go next and finish. Next and finish. And then open your simulation and go to the XML. In the XML, you can start doing these changes, but before I go there, I will help Kimberly to set it up. So basically, Kimberly, what you need is this over here, and I will paste in the chat and also
Okay.
show you how you could get this without any assistance. But first, please make sure you copy and paste it. Copy and paste it to make sure there is no mistakes. So inside your...
Just a quick question. The constant concentration, is it like an initial value along the median, or is it a value that will always be 100 in every voxel of the median?
Second option.
Second option. It's always 100.
Yes.
Perfect.
Yes.
Thank you. Thank you.
No problem. All right. So let's say, Kimberly, you don't have my assistance and you want to do this from scratch. What I will do is CC3D ML, plugins, secretion plugin, and then I will do this, comment out and add. And here you get this brand new secretion plugin with many options. So here you have a constant concentration option, which is the one we had. And then you will do type medium, and then you will do 100 here, 100.0. And then you will delete these two, and that's it. Got it?
Kind of.
Okay, I will go through it again.
It's okay. Yeah. Oh, yeah. Okay.
So code snippets, this is important. CC3D ML, then plugin, secretion. Comment alt and add or replace, it doesn't matter. Now here it gave me a block, the secretion block, with many options here inside.
Secretion was what? It was secretion. Which one was it that you did grabbed?
What?
Which one was that you grabbed? Secretion and then what?
Yeah, secretion.
There's like 15 options.
No, you are in the wrong place. So it's CC3D ML.
Plugins. Okay, got it. Okay,
Yes. And then
okay.
secretion. Yes.
Formed. Mine says not well formed. Do I need to have my cursor or
You don't need to do that. Just stick to the one I gave you, like I pasted in the chat.
Okay.
All right.
In that markup language, it's very important that you not paste something inside of a block of something else.
Oh.
So if you go inside of a plugin and paste in another plugin, that will fail. So look for example, look at line 56 where it says end plugin. And there's a blank line. Put in a few blank lines and then paste something in there.
Oh, okay.
If you pasted something in, for example, in line 70 inside of a steppable, Or
Yeah.
after 62
It'll
inside of
crash.
plugin, it will crash.
Okay.
Okay.
So while I was giving these instructions, I hope you guys changed these parameters as said in the slide, and I will start doing it myself now. So global diffusion constant 10. So here I find my diffusion solver FE, and I found my global diffusion constant. I'll change it to 10. So again, in the XML, I found the steppable diffusion solver FE. I found the diffusion field neutral, and then I found the global diffusion constant, and I changed it to 10. Second parameter, the global decay constant right below it, 0.01.
And why did we put 100 before?
Constant concentration on 100. Why did we put 100?
Okay, I see.
So
Thank you. Sorry, I was too
Okay,
fast
no
in shutting.
yeah, so constant concentration 100 right here. I will copy and paste this in the chat again for you guys to make sure it's exactly the same. So you should copy that in the chat and paste in a blank isolated region of your XML. Now continuing, global diffusion constant 10, global decay constant 0.1, and it tells us to comment out diffusions and decays for specific cells. So I have this from line 77 to line 82, I have cell-specific diffusion coefficient and cell-specific decay coefficient. So I will comment them out like this, control slash, control slash, control slash, control slash, control slash. Yes, so the last step was commenting out all cell-specific parameters. So you can see here in my code from line 77 to line 82, I have this diffusion coefficient for cell type and decay coefficient for cell type. I click Control and slash in each of those lines to comment them out. You don't, you initial concentration is right here, but we are not using initial concentration. The initial concentration is stays commented. Okay, we are not changing it. So now I will what am I going to do? Comment out secretion lines inside the diffusion steppables. Okay, so inside the diffusion steppables, there are these 3 secretion lines.
Which line we should comment?
Cell-specific diffusion coefficient and cell-specific decay coefficient, all of them. And then all the secretion lines inside the diffusion steppables block.
Why
So
are
I
you,
will do it one more time. Go ahead, Sharon.
why are you referring to those lines as steppables? I thought that referred to the Python. No.
So it is steppable. It's written right here.
Oh, I see.
Yeah.
I think it's SML file we're commenting on.
XML. Yes. In the XML. Yes.
And why do we comment them out?
Because we don't need them and they will
Yeah.
interfere if we leave them.
Why don't we need them? How do we know that we don't need them?
We don't need well, because the exercise is designed this way, and so this is the answer already. But I could be doing a more blind exercise where you figure out that you don't need them, but that's more that requires much more time for us.
Okay, so the reason why we comment them out is because the cells don't talk to each other, actually.
They do talk to each other, but they have the same, they will all use the same decay constant. A field will decay on them, and that's all. Very simple, very, very simple simplification. I mean, simple simplification,
Okay,
very
so
hard
if
simplification.
if we set the global constant and we do not specify what any cell is doing, the global concept is taken for all cells. And if we
Yes.
specify a cell having a decay constant of 0.5, this will be an exception in all the cells we have, because all others will stay with 0.01.
Yes,
Mhm.
exactly.
Thank you.
I have a question.
Go
So
ahead.
in the slide, you were mentioning that we need to set the initial concentration to 100, but in line 75, you commented that out, right?
Oh, good. Yes, I did not reach that yet, so that's why.
Okay.
Yeah, I'm sorry.
I have one. Oh, sorry.
Go
I
ahead.
have one question is we set the global diffusion constant at 10. If we don't comment out the, for example, the prolif cell, we set it to 0.1. So does it mean that the rest of the cells will be 10, but we specialize for the prolif cell to be 0.1?
Yes.
Okay, great. Thank you.
So now in the secretion section inside the diffusion block, okay, inside the diffusion block, there is 3 secretion lines. Go ahead and comment them out too by hitting Control/ or Command/. Okay. Now set both periodic boundary conditions to periodic, and I will do so by commenting unnecessary and uncommenting the necessary. Using the command Control/. I will do that again if in case you missed. So this is how my boundary conditions were initially. And then I place my cursor in a line and hit Control/, and then Control/. So now I have no boundary conditions in X, but here is the periodic one, Control/ on that one to uncomment. And the X boundary condition is good to go. I will now do the same for Y. So comment, comment, uncomment.
So in the pots also there is a boundary X periodic, boundary Y periodic setting. How is that different from this setting of periodic boundary?
This one
Or
is
periodic condition?
for the diffusive field. The other one is for the cells.
Oh, thanks.
In general, we set them the same, but you can set them separately because the two lattices are different entities altogether.
I have a question.
Go ahead.
I think you mentioned this, but it would be great if you could say this again. So why are the boundaries periodic? Man? Why is it not
It doesn't make a big difference in our simulation here.
okay? So you are just assuming this condition, right?
Sorry?
So are you just assuming this just for the sake of this demonstration, or are the periodic boundaries are really periodic in nature, in reality?
There is no periodic boundary condition in nature unless our universe has a spherical shape.
Yep, that is what I was thinking. Okay.
Yes. So the periodic condition is an approximation for an infinite lattice.
Yes. Okay. Thank you.
So finally, in the blob initializer, you would set with 8, and create only prolif cells. So here, I'm deleting Quiescent and Necro and leaving only Prolif. Make sure you don't leave any commas behind. Okay. How are you guys doing with the exercise? Do you need more time? And I should also add that this is also a minimalistic model. So when we talk about minimalistic models, we are giving up on realism to identify what is the underlying mechanism responsible for achieving a certain outcome.
Why did you select?
Finally,
Sorry.
sorry.
Sorry, go ahead. I had a question. So what is the reason for selecting only the proliferating cells in the blob initializer?
For deleting all of them?
Yeah.
Well, because I am assuming as an initial condition that all tumor cells are proliferating.
Okay.
Yeah, this would be in the model structure. So it doesn't make sense if your tumor start out necrotic, right?
Yeah. Okay.
So all cells are starting with a proliferating phenotype. So final change, as I was reminded, because I'm also lacking brain cells already. Initial concentration to 100. So find the initial concentration line, change that to 100. Yeah. Okay, I will launch the poll to see how you guys are doing with this. All right,
Oh,
I will proceed.
maybe I misunderstood why we set the constant concentration in the secretion plugin to 100, and then we set the initial concentration expression to 100 also. Are they different? How are they different?
They are different. So when you set the initial concentration expression to 100, that's the initial condition of the field. When you set constant concentration to 100, it means that all the time, no matter what happens, medium pixels will have the fixed value of 100 concentration.
Oh, okay, got it.
I have a question. It is possible that can we let the diffusions this kind of, what is the name, field to decay along with the simulation time? Is there any way to do it?
Yes, we are already doing it.
Oh,
by setting.
Okay, please go ahead.
Okay.
Okay. See, if there's a decay constant. Thank you. I didn't notice. Thank you so much.
The field will never decay in the medium though, because medium is constant concentration 100 always.
I'm asking about the medium.
Okay, so if you want the field to decay in the medium, you would have to remodel everything. You have to restructure your model because constant concentration 100 is inconsistent with the outcome of the field decay in the medium.
Okay.
So it would require a different model structure altogether. But yes, it is possible.
That's interesting. Thank you.
Okay, so I will proceed. And more cleanup stuff in the steppables.py. So now it's the steppables.py file, okay, in the Python file. You will find these target volume and lambda volume parameters. And it's telling us to set the target volume to 64 and the lambda volume to 8.
Maybe it's useful to remind people why you're doing these things. So you've created an initial condition. Now you're going to have the cells have an initial volume, target volume, and then you're going to have the cells grow depending on what they're experiencing and transition between quiescent, proliferating quiescent, or proliferating to necrotic. And so you have to set rules for all of those things.
Perfect. So this, what we are doing is setting the initial target volume and lambda volume for all cells. After doing that, so line 14 and 15, after setting 64 for target volume and 8 for lambda volume, find the division function in the mitosis tuplables. So there is this update attributes function, like scroll all the way down and you will find this block here, which states that if self-parent cell is 1, child cell is 2, else child cell is 1. So what you want to do here is get rid of this piece of code. You can delete it, only these 4 lines, or comment it out by using the command Ctrl/. So what this piece of code is doing initially is changing the type of the child cell, and we don't want that. We want the child cells to be the same type of the parent cell. So we are disabling this garbage, not garbage always, but for our simulation, this is garbage. So get rid of this piece of code.
So maybe a different way to say that, Pedro, maybe a little less negative, would be that the template code is there to show you what you can do with these modules.
Mhm.
But you have to think carefully about what it is you want to do. And so sometimes the template code will show you possibilities, but there are going to be some code snippets where you have to choose. It'll say, pick one of the following three things. And if you leave them all turned on, it won't work. And similarly, the code here is showing you how you can change the cell type on division, which would happen, for example, for a stem cell. But you have to think carefully about what it is you want your simulation to be doing. If you want your proliferating cells to stay proliferating, and only the proliferating cells are going to grow and divide, so you're only talking about proliferating cells here, then you don't want to change the type after division. In reality, biologically, cells might very well become quiescent after division and have to re-trigger the cell cycle. In that case, you would change all of the cells after division to a different type. So again, here we're jumping ahead and doing the coding directly. But if we thought carefully about what the model was, we might make slightly different decisions. Here, it's again more of an illustration about how you can build a model of this kind. And so we have to take some of these things as given in the context of the demonstration that Pedro is going through.
Next step is finding the division threshold. Hopefully, you learned that during Gilberto's class. So cell volume greater than 50, cells divide. We want that to be double the target volume of cells, the initial target volume. So instead of 50, we want 128, 128, 2 times 64. So make sure you made the changes in the slide, and I will relaunch the poll to keep track of how you guys are doing with it.
Pedro, the lambda at the very beginning is a float, and you put in a number. I don't.
Yeah, in the Python it doesn't matter, but you can do both.
Okay. Thank you.
No problem.
Excuse me, I have one question. Is why do you choose? What's the reason that you choose 64 as a target volume?
It's arbitrary. There is no special reason for that.
So there's no relation between your simulation with the experimental data that you want to.
No.
Okay.
This is an archetype. It can be worked. Someone can take the simulation and work on it further to make it compatible with experiments, and this would be a reasonable hackathon project. So if you were interested in doing a hackathon project on a vascular tumor that fits experimental data, that's perfectly possible, straightforward, I would say. And this specific exercise it's not intended to accomplish this goal.
And what's the units of the target volume? So we can relate to. Okay.
So if you want to relate this to biological measurements, you will have to make associations. For example, I will assume that 64 pixels are equivalent to 10 microns, and then you work from there.
Oh, okay. Interesting.
By creating these equivalences, or for example, you can map Monte Carlo step to hours by saying, oh, my cells take 24 hours to divide, so I will measure the time my cells on average take to divide, and I will say, okay, 100 Monte Carlo steps are equivalent to 10 hours, for example.
Yeah, makes sense. Thank you.
Okay.
Could I interject something?
Sorry?
Could I interject something quick? Just want to point out, it's not entirely arbitrary, that 64. In some of the simulations we've done, we have an initial size which doesn't match the target volume, so that when you first start up the simulation, it either grows or it shrinks. Whereas here you had set up an initial width of your cells in your uniform initializer of 8, which means they initially had a volume, since they're square, of 64.
Yeah.
So what you've done is you've made it so that their target volume is in fact their volume when they start.
Perfect. That's correct. It's not entirely arbitrary, but I could have done, for example, 49 and 7. But yes, as Sharon pointed out, this 64 here is consistent with this 8 here. Okay, so now we are able to run the simulation, and you should see your cells growing and dividing, just like the early demos in the growth and division class.
Can you get simplified graphs, one showing cell field and one showing nutrient?
Yeah. Your graphics file. Like this?
Yeah. How'd you do it?
Window, new graphics window,
Okay.
and then tile. And then you choose
okay.
one window to show cell field, the other to show field.
So cool.
Why do the growth mitosis projects not have the avascular tumor steppables? Well, the name is arbitrary, Kishore.
Like, I want to ask, like the default steppable class was there when you don't add these plugins, right?
Huh?
For every project, if you don't add these mitosis of truth or other plugins, then there is a default steppable class, right? Which is essentially the project name steppable. Don't worry about it. We can think about it later.
Yeah. I mean, these steppables, these classes were initialized because we selected certain plugins in the wizard. If we did not, it would have generated a customized class for us with the title of the project.
Yeah.
So the names don't matter as long as they are consistent with the calling of the steppables during the registration of the steppables.
Okay.
Okay, so
Thanks.
were you able to run the simulation, and is your result similar to mine? So you should see field everywhere, like my simulation.
I have got similar result, but in the cell type colors, it isn't showing any necrotic cells in my simulation. Although I have added.
Can you repeat the problem?
So Pedro, two things. One, people have to remember to change the scaling on the concentration windows.
Okay, that's one. Okay,
and
so
two,
please,
you haven't changed you have not yet put in code that will change the cells from proliferating to quiescent or necrotic.
Yes.
So at the moment you have proliferating cells, they proliferate, and that's all that happens.
Yeah.
So there isn't any way that you would see quiescent or necrotic cells because you haven't given instructions or rules for how to create them yet.
Yeah. So why are we? Okay. So please, people, go to Tools and Configuration, and here, what I'm using is unfixed maximum range for field visualization. Okay. So for my field nurture, I have unfixed maximum field, and so that when the field decreases, red is still the maximum available in the in the That's correct. So Susan got it correct. Masa seems to have gotten it correct too. Good. So I will launch the poll one more time. Or else, who could not get this?
I
Okay.
still have what I posted.
Okay, so maybe the reason is in XML, make sure you have this chunk of code, plugin secretion, with 100 constant concentration in medium. Make
Yes.
sure that's
Field name nutrition, constant concentration type medium 100.
so. Can someone go to a breakout room with Katrin, please, to take a better look? Otherwise, we'll run out of time here.
Which breakout? I can go there.
So
Breakout.
let's go to room 3. It's empty at the moment.
Right. So please, Roberto,
Which room? 1?
3, room
Ah,
3.
3.
Yeah.
Okay.
All right, so for the folks here, now we are going to implement the transition, the state transition of cells from proliferating to quiescent, quiescent to proliferating, and from proliferating to dead. So here the idea is the cells are sensing this nutrient field, and if this nutrient field is above a certain threshold, they are proliferating. If it's below a certain threshold, they go quiescent. And if it's below another threshold, a lower, even lower threshold, they transition from quiescent to necrotic. So that's the basic idea. Again, this is not the most realistic model for a vascular tumor, but this is simple enough for us to do. It's straightforward. So what you want to do is go into your steppables Python file, and inside the growth steppables, get rid of line 24 loop. So get rid of that, and instead of that, as following the slides instructions, you will loop over cell types. So you can acquire this code snippet by coming Anj Gupta, do you have a question? Anj Gupta, do you have a question?
Okay, great.
Okay.
Thank you.
All right. So instead of that for loop, you want to loop over cell list by types, and you want 2 of them so far. So one for loop for type prolif and another for loop for type quiesce. And you do that by going to CC3D Python and then visit, and then all cells of given type right here. And then it generates this for loop for us. And as the slides tell, we will duplicate this chunk of code to have 2 loops. The first loop, we want it to be over cell type prolif. So let me get rid of this altogether. Okay. So in the first for loop, replace the arguments with prolif, like this, self.prolif. And on the second for loop, replace the arguments with self.quiesce.
Quick question. So originally in the code, it had commas and like type name 1, 2, 3. So that would have been if we wanted to have that loop performed over all the cell types. Got it.
Yes, you can loop over a set of cell types. So why are we doing this? Because we need to specify dynamics and interactions for specific cell types. So that's why we loop over cell types. Yes, kind reminder from Lou. All capital letters. So next step is first getting the field object. Why? Because we want to test if the concentration of the field is high or low in a given cell to decide whether or not we want to change its state or change its type to either proliferating, necrotic, or quiescent. So go ahead and acquire that field object, and you do this by creating a variable called field, and then an instance of the field self.field.neutr. Then neutr has to be exactly the name. Neutr is the name of the field. It has to be consistent with the XML settings. After that, we will acquire the concentration of the field at the center of mass of cells. So we'll do this for prolif and for quiesce cell types. So concentration at, oh, there is a better way of doing this. So we'll use the code snippets again. So CC3D Python and fields, chemical fields manipulation, get field value. That's it. So if you go to Python, chemical field manipulation, and CC3D Python menu, the drop-down menu, and then chemical field manipulation, get field value, you will acquire this piece of code here, which doesn't help. Let me see if I can find a better one. Well, okay. I'll have to type this. So concentration at COM is field. And here, instead of using this 10-10-0, which is the default, we use the cell center of mass vector, which is cell.x.com, cell.y.com, and cell.z.com. ZCOM. So I will copy and paste this in the chat. This has to be inside your for loop. Delete the prints, yes. Get rid of the prints. You can get rid of these comments. And we want this concentration at center of mass inside both for loops. So that's how you acquire the field concentration at the cell center of mass. Next,
Pedro, there's in the commented field that we just deleted, it looks really similar to what we just typed, with the exception of a lack of INT. What would that do if we had INT?
Huh?
I can put it in the chat.
Okay. I think I know. Maybe you got the code snippet, correct?
No, it's just default. It's a comment. You deleted it, but
oh, I deleted it. Okay. It doesn't make that difference. Don't worry.
It doesn't make any difference? Oh, okay.
No. Yeah, it just makes it an integer. Yeah, maybe mine crashes and then I have to do that, but I hope not. I just deleted comments. All right, so next step is testing using thresholds to test if the concentration is high or low. And then based on that, we decide whether or not we want to change the cell type. So in our loop over proliferating cells, if the concentration is lower than 70, we change type to quiescent. And if not, if the concentration is not smaller than 70, we allow the cell to grow by doing cell.target volume plus equals 0.5. And then in the quiescent for loop, we will test if the concentration is above 70. If it's above 70, we will change the cell type to prolif because the transition is reversible. And if the concentration is lower than 40, we'll change the type to necro, which means the cell is going to die. So here I'm gonna do if, then copy and paste this one. If concentration is lower than 70, then I change the cell type. So I do cell.type equals self.quiesce. This is how you change the type of a cell. Cell.type is its type, and then you assign a different type. In this case, self.quiesce means that the prolif cell will change its type to quiesce. Else, so if the cell is okay, increase the target volume. So cell.target volume, uppercase V, plus equals 0.5.
You have an extra V in line 27.
Oh, thank you. Nice. Now we'll do basically it's the same idea for quiesced cells. So if concentration at COM, I could have just copied and pasted. I'm dumb. More than 70. Now this is the reversible transition. We do cell.type equals what?
Prolif.
Good, prolif, perfect. Self.prolif, like this. And if concentration is below another threshold, so concentration at COM is below 40 in this example, we do cell.type equals self.necro. And then we set the target volume to 0 to make sure it shrinks. I will copy and paste this in the chat. So if you guys are having difficulties to follow, you can just copy and paste it. So the dead cells are leaving the system, slowly leaving the system. Yes, slowly disappearing. I will go ahead and run this. So let me see what I got before I ask you guys how you are doing, because I could have made a mistake. So they are growing, nutrient is depleting inside the blob, cells are becoming quiescent, and it's depleting. It's going to green. Once it gets to blue, they will start dying. Still growing. Now, finally, cells started to die, and we see the necrotic core shrinking as the tumor tries to expand. So I'll go back to this so you guys can see. Let me just pause the simulation. You guys can see the final instructions, and I will relaunch the poll to see how you guys are doing with it. Again, this is not supposed to be a realistic simulation. As I was explaining, it can be transformed into a realistic simulation, and this would be an amazing hackathon project with possibly a publication out of it. And I already have results, the experimental results. Not me, they're not my experimental results. I have some papers that measured, for example, field profile in tumor, in the avascular tumor in vitro. So how are you guys doing with it?
In my simulation, the necrotic cores and the quiescent are all the same color for some reason.
I think you don't have necrotic cells then in your simulation. Go to your XML and check if you have the necrotic type in your cell type list. So like here, I have medium, prolif, quiesce, and necro. You should have all of them.
I do have all of them.
Okay, so you have all of them.
Yeah. Would it be possible to share my screen?
Yes, go ahead.
So here it is. So if you go to this, there are only 3 types, but if I go to this, I have.
Can you run it? Because it seems correct in the player. So let's see how it is. Run that and because it seems correct what you have there.
No, I only have 3.
It shows, so in your cell type colors it doesn't show the necrotic. I don't know why, but your simulation seems correct. So I think this is not a problem in your code. It's another problem that I don't know how to address it. Go ahead,
Were there
James.
people, Katrin, did you want to screen share to see what's
Yeah,
going on?
maybe. Yeah, Katrin, please screen share. Let's see what's going on.
Yeah, I'll do so. Moment. Meanwhile, I played a little bit, and now I have very interesting thing. Look at this. Can you see my screen?
Yes.
Yeah. So
Okay, that looks good. It looks good.
that's the other way around. And let me tell you, I made it when I crossed out this line. The initial
Okay, makes sense.
the initial concentration.
Okay.
And when I activate this line again and just so nothing happens.
Wait. Let it run. Let it run. Let's see.
Nothing happens because the concentration is here and here the same, and here nothing happens. Minimal and maximal concentration is 100.
Oh, okay, that makes sense. So go to tools.
This is something I tried already, and when I fix both of them like this, and I repeat, I get a nice colorful thing here, but
they're all 100. Okay, it makes sense. So go
still
to your
no
XML. I
diffusion.
already know what it is. Yeah, go to your XML. Scroll up. Scroll down. Okay. Do you know what it is, James? I don't know.
Well, you were having trouble with the diffusion constant not being what you expected it to be. Was that right?
Yes.
So my guess is that what's happening here is that somehow the uptake rate isn't quite what we think it is either. Let's try taking. Let's start out with.
Hello?
No, sorry. So before we go there, when you set the medium, when you set the initial concentration to 0.
Susan, do you have a question?
Here, 0. No, I guess she is.
Set the initial concentration to 0, and let's just look at the chemical field.
So
let's
like
ask the question: is the medium secreting or not? Yes, that's right. Let's run that.
That's the only thing, okay.
And let's just look at the chemical field. The cells will disappear, but let's look at the chemical field. So the chemical field is now correct.
Yes.
Right? You see that it starts out only in the medium and then is going into the center. So the chemical field is working for this. Let's try running this again and just stepping through it rather than actually hitting run. Let's just go step, 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 see what it does. So you see here initially, you see the chemical diffusing in, so diffusion is working. And the cells are seeing a low chemical concentration, so they're dying. So that looks pretty reasonable. So now what we have to do is that the chemical field is working. What we need to do is look at the rules and see what we're taking up. What is the amount of chemical that the cells are seeing? So now let's look in the Python. And let's see what you're doing. You're reading concentration at COM. And I'd like to see whether we're actually seeing. So let us do one thing first. Let's So it looks like the decay is not working, is what's happening. The
Yeah,
decay,
but then in the XML it looks okay.
not working. No, but the decay coefficient isn't working, is what's happening here.
Oh.
So that's seems to be the problem. Just the way her diffusion coefficient doesn't seem to be giving the right results. The decay rate is not working.
Where
So
it's
that's
not
in
here.
the XML. It's in the XML.
So maybe increase it a lot. Put 10 instead in
Let's just
global
make
decay.
it, well, you making it bigger than 1 may crash the code, but let's make it 0.1 and just run it again and see what happens.
This we
true.
tried already and it's not working. Should I put this one back to 100?
No, let's not make it 100 yet. I want to see what the diffusion field is doing first. Make sure it's behaving right. Okay, what's the maximum and minimum value of the field? I can't read it from the screen.
0 and 100.
Okay, so it is correct. Okay. So that's behaving normally. All right. So now, okay, let's now try setting the initial concentration back to 100.
And then
There's
it doesn't
no
decay.
decay.
What is going on? There's something wrong with her version of CompuCell.
Mhm. What if we initialize the field at value at 10 instead of 100? What happens? Hit pause. No, stop it and start again. And just hit step instead of run. Okay, what is the minimum and maximum value of the field?
Still 0 and 100.
Okay. So it is correctly overwriting that initial value. So that's puzzling to me. Okay.
Let's try, instead of using global diffusion, let's try the cell-specific one. That would be my last attempt.
Other people have questions, maybe also.
Yeah.
This maybe we should do. If other people are having the same problem, we should do it here. If people see people are getting interesting cell shapes now.
Yeah. Okay, so people feel free to interrupt us. In the meanwhile, yes, try that. I will just, save and try. That's it. Oh, it looks like it's working now. Try now putting 100 as the initial condition.
This is crossed out.
Yeah.
So this should be activated again.
Yes.
And then 100.
100. Yes, let's see. I saw it's bluer now. Yeah, I don't know. I think Maciek should meet with her.
Yeah. Okay, so I stopped the screen sharing for the other questions. But thank you anyway.
Yeah, I'm sorry. It's probably not a problem in your coding. It's not a problem in your simulation. I think there's something off with your specific version of CompuCell, or I don't know. So this is officially Q&A, I would say, because we are running over time already. Just quickly, this simulation can be developed further, and one of the implementations you can make is the nutrient-based growth, which is you let your cells take up nutrient, and based on how much they take up, you let them grow. So the growth would be proportional to how much they consumed of nutrients. And if you want to develop this simulation further, I would recommend you taking a look at Douglas Hanahan paper on the hallmarks of cancer. And I will launch the questionnaire so you guys can give us feedback. Module experience questionnaire. Was it launched already? I don't know. Okay. I would appreciate if you guys could give your feedback, please. Take a moment to write your suggestions if you have any. And this is officially Q&A now. So if you need help or if you have questions about the exercise or anything else about the workshop, please feel free to speak.
I've got a question. And maybe yours is behaving this way, but I didn't see it. It wasn't up for very long when it was running. And I haven't seen this in anything else that's been on the Zoom screen. But mine has some very interesting dynamics, developing lobes and holes, and the necro cells kind of all die and the new ones form. Is that normal?
Yes, it is.
It shouldn't stay round. Okay.
Yes. No. It's a very unstable shape.
Yeah.
And yeah, exactly. It's fantastic. And there is a very cool exercise you can do with this, Sharon, which is if you set regions of space with different concentrations of field, the trend is that the tumor will grow to the side with more concentration and shrink in the side with less. And then the tumor will start migrating towards like a collective chemotaxis,
right,
without any movement.
Sure.
Explicit. So if you want to keep developing the simulation, James is asking me to head back to this slide. This is what you can do. It's the nutrient-based growth. You let your cells take up the nutrient instead of just telling the field to decay in the cells. And then based on how much they take up, you adjust the growth rate.
Did we have decay in this?
Yeah, we were using decay. Certificates. Question about certificates.
Oh.
Pedro, is this another exercise? Sorry, I just jumped from a break room. Is this another option?
No, No, it's not. This is something you, if you are super interested in the simulation, that's something extra you can work on.
Why don't you put it back up on the screen? You just took it down, Pedro.
Yeah, because it's people shouldn't think this is activity. This is not an
I say
activity
let's
going on. That's what I mean.
let's add a cell type, two different cell types with different phenotypes, macrophages inside outside the tumor and phenotypes inside the tumor, macrophages inside the tumor.
You can
That
do
would
that,
be a
yes.
great exercise, yes.
Yeah.
You could certainly have macrophages that seek out the tumor and kill tumor cells, or and the tumor could secrete, for example, something that allows immune avoidance.
Yeah.
Again, this is a very simple demonstration of the basics, and you have to do a fair amount of work to take this simple simulation into something more realistic. Although you still, as Sharon pointed out, you still get non-trivial tumor shapes, subdivision of the tumor. And so you can actually build a pretty realistic model starting from this.
I want to see the classic tumor that develops teeth and hair.
A good challenge here is, for example, making the tumor grow symmetrically by tuning the parameters. This is a fairly challenging exercise.
Is this your screen, Pedro?
Yes, this is my screen.
My simulation has yet to get any necrotic cells. I wonder if I was in the back in my chair just broke. In a breakout room. Did you change any parameters from the concentrations that were from the last thing we went through?
No.
Or wait. Huh.
So
Yeah.
let me show you my code here. This is, so after the XML changes, this is the piece of code we have. Do you have this?
Yeah.
Fully?
Yeah.
Do you have 128 here?
Yeah.
Do you have 64 and 8?
Yeah.
Do you have the three cell types, Necro, Quiescent, Prolif?
Yeah.
Do you have constant concentration in medium 100?
I tried to adjust that in the XML. Let's see. Or wait, no, not in the, yeah, in the secretion field. Plugin. Constant concentration type medium 100. Yeah.
Okay. Let's jump to the diffusion solver. Do you have global diffusion 10 and decay 0.01?
Global diffusion is 10 and decay is 0.01. Yeah. And I had initial concentration expression of 100.
Okay. Well, so let you share the screen and
okay.
Let's see.
For some reason, I really like this. I really like this exercise.
Yeah, it's fantastic.
Okay, can you see?
Yes. So show me your simulation running.
Okay, yeah.
Yeah. Okay. Okay. Oh, there we go.
Oh, I
Go to
swear I
your-
wasn't.
Yeah. So
It
go
was
to your
frozen
snappables.
almost.
Go
Even
to
though
your
yours
snappables
is
now.
okay. Yours looked a little different. That's really strange that it looked like it had gotten frozen, but I hadn't changed anything. That's weird. Okay.
Snappables, the snappables file, the Python file. Yeah. Okay. Okay, so line 41 and 42, delete those. Delete the 2 lines. 41 and
Oh,
42.
okay.
Yeah. Okay,
That
that
makes
one
more
was quick.
sense. Okay. Yeah.
Now run again.
I have to stop this.
Mhm.
This looks more like
And
it was.
let
Well, okay.
let it run for a bit.
Cool. Okay.
Yeah, this is exactly
Yeah.
what I have. Yeah.
Okay. Cool.
Perfect. We're still in Q&A. You can ask more questions if you want before we break.
Nutrient-based growth.
In the meanwhile, this is how my tumor looks like. I love the simulation so much, and it's not even close. And I like it the way it is, wrong. I like it wrong. I like it inaccurate. That's how I like it. No biological meaning here.
Can you change it to be 3D? Would that be interesting or would that be
Let me try
confusing
that.
because
Let me
there's
try.
things happening differently in the different layers?
I'll try.
So
I'll try.
cross section's better.
That's also a good demonstration exercise. So how I will do it is first we'll have the settings. I will also reduce the lattice because it is much more expensive to have a 3D simulation. I will add a periodic for Z. Z. I will now go straight to the initializer. In the initializer, I will do a smaller radius. And in the center, so 25, 25, 25. And now in the steppables, I have to look for anything that relates to positions. So this relates to positions, and this is correct. X com, Y com, Z com. And that looks okay. So I will run the simulation. That makes sense. So this is my simulation. Let's see what happens.
Yeah, you can't see inside.
Yeah, you can see inside by cutting it.
Oh.
And you can choose an appropriate slice to see your tumor. So self-field and play. Let's leave it 25. Yeah, and whenever you change the settings, it goes to space. See you, Catherine. Thank you. Have a good sleep.
Can you change the Z stack?
Yes, I was changing by hitting these arrows here. Yes. So it is beautifully growing. Let's see if we will see. I mean, it's changing from 2D to 3D is definitely not a intuitive, like there is no guarantee that it will behave the same way. Absolutely no guarantee. And that's true in nature too. So if you grow a plant in 2D, it's extremely different from growing a plant in 3D. if you grow a cell culture in 2D is extremely different from 3D, so on and so forth. So,
Oh, can we check the code again? Like you'd think that you would think that the nutrient concentration would still be
Pedro,
different.
I think you need to change the target volume because volume in 3D is kind of bigger.
It's not a problem. So far it's working great. I don't see any problem here. The only thing is that it's going to take a while to see the inner cells because it's 3D, it takes a long time to grow. And you still need the same distance from surface to center to see the quiescent and necrotic cells. So
does the Monte Carlo step
simulation,
does it take, you're saying it takes just longer to make each Monte Carlo step?
both. I'm saying
Okay.
both.
Okay.
And let me also update screen every 100 so that it's a bit faster.
Pedro, can you show your XML file? Like, how did you set the XY 3D simulation?
Yeah.
Thank you.
And in the meanwhile, I already changed it to increase the simulation to 100 by 100 by 100. So in the dimensions in pots, I changed the dimensions to be 3D. So Z has to be a number greater than 1. Then I changed the initializing region, the initialized region here. So now I'm centralizing it again. And I will do another thing here. I will change the size of the cells to be smaller. No, I'm not doing that. I regret. And that should be enough.
You don't need to also put the PPC in the zeta axis?
Yes, sure. You need to do that too. Yes.
The what was that? You do what in the zeta? What was the question?
Boundary condition in the
Yes.
zeta.
You always
yeah,
need to
okay.
change the boundary conditions, yes.
And you
So
have to
because
a cell to be in the middle of the simulation.
With the region, right?
yeah.
Right.
Yeah, this is gonna take a long time. So this is why most of our simulations are in 2D, because in 3D you'll have like 100 times more pixels, which means 100 times more Monte Carlo steps. I mean, no, 100 times more pixel copy attempts per Monte Carlo step, which means your simulation is 100 times lower.
Oh.
So in general, we don't need to touch the steppable Python script file, right? We just need to modify the XML.
Yeah, in general, depends on how you write positions in your steppables.
I'm sorry, can you show the XML again? I didn't follow. Sorry.
Which part?
I would just like to add that your volume in 2D is area, and in 3D you have one more size to multiply, so maybe you need to adjust that.
Yes, that's true. Yeah, that's true. But I chose to not adjust that because it will change something, but like not much, So I just ignore that for now. But yes, so if you have a size of 50 in 2D and you go to 3D with still a size 50, the radius will be smaller in 3D. So if you want to preserve cell radius, you have to rescale the volume when you change from 2D to 3D. So is that okay, Huixia?
Oh yeah,
I'm sorry, how do you pronounce your name?
it's Huisha. Thank you.
Huixia? Huixia?
Yes,
Huixia.
thank you
Okay.
so much.
Huixia. So I wanted to study a bit about implementing reaction diffusion fields inside the cells. Would you have any recommendations on readings or papers? James has.
I
And
guess the question for that is what is it you want to do with a reaction diffusion field? So
maybe curiosity.
So what I want to do is I wanted to solve for intracellular dynamics, mainly focus on the RAC protein. That basically happens there's some reactions and with activation and deactivation that happen only inside of the cell. And I kind of wanted to do that. I know it's possible with finite elements. I usually do this stuff on Morpheus, but Morpheus doesn't like solving things in 2D moving cells. So I was wondering if I could do that in CompuCell, basically.
well, if it exists I mean, Morpheus has some features that CompuCell doesn't have. You can do diffusion on the surface of the cell in Morpheus, which you can't do in CompuCell.
Yeah, what I do there is to solve on the cell's membrane, but that becomes like a 1D in space. And I wanted to solve that in a 2-dimension space on the deforming geometry of the cell. Is that possible?
Well, no, CompuCell only will solve the reaction diffusion equation on the lattice. So
Okay.
there's no advection. Now, if the decay terms are fairly fast, that doesn't matter. Again, it depends a little bit on the details of what you're trying to do. What you can do with rack and row would be to use the kind of simulation method that Julia will show us later in the week.
Okay.
Where you represent the chemicals explicitly as subcell objects.
Okay.
Could probably do it that way. So
And that'll be later this week. Okay.
I would talk about it with Julio as a possibility.
Perfect.
You certainly can turn on the reaction diffusion solver and solve reaction diffusion equations inside of cells, but there's no advection. And so if the cell moves, it will have to adjust by the decay term in the reaction diffusion solver.
That makes sense. Thank you.
Yeah, you got it right. Go ahead.
If you wanted to get to add the Morpheus advection solvers to CompuCell, we'd be delighted to do that. We would love to have those.
In Morpheus, the team there is still figured out some advection stuff. They don't have advection yet. What I do is you kind of you create a different space where you solve, pretending that that's the cell edge, and then you import back to the CPM. You can translate things back from the CPM to the model like tension, but it's basically solving PDs separately from the CPM, and then they interact at every step.
So you could do the same thing here. If you call Phoenix or some other Python, or if you call a Python library to do the PDEs, you could do that. It's going to be slow.
Yeah. No, but that makes sense. Yeah. Now you gave me a good idea to implement with Phoenix, because then I can do probably a CPM iteration, solve something in Phoenix, return to the CPM.
Yeah, cool. I think that's the best bet for this.
That's pretty cool.
Because if you use Phoenix, you can have full hydrodynamics, fancy reaction diffusion equation.
And I've already done that in Phoenix with the models that I work on, so that will be easy to implement too. That's kind of cool. Thanks for the idea.
That's how I do it, and you can read. Where I shared, I think this explanation that Maciek did last year of how to call from the C++ how to call things too. it's a little more work, but if you're already using Phoenix, you've got a level of sophistication where that wouldn't be too hard. And then things might run faster, or you can interface through the Python layer. They're both possible.
Yeah, that's really good. That's really
Probably
good.
not gonna, we're not going to cover that this week. It's a little bit too
No, I
complicated.
think with the Jupyter notebook stuff from today, it's somewhat possible to start playing around the area for sure.
If you're comfortable with that, then it's doable,
Yeah.
very doable.
Yeah. Thank you.
I was thinking, I don't remember I don't know if you remember last year I was trying to model like nanofilm grown bubbles under heavy ion irradiation.
Yes.
And yeah, and now the model actually now creates like hot cylinders where the ion passes, but what I am doing is changing the flux amp of every cell inside the cylinder. But I was thinking if maybe it's not better to create a field that starts diffusing over a single line, you know, like. And is there any advantage of doing that? Maybe I could, you know, make a better use of the tools of CompuCell, because flux amp doesn't mean like temperature, you know. I was thinking if maybe the field of temperature would be like redundant, or no redundant, maybe flux amp is almost temperature, then I create a field for temperature. So I don't know if it's a good idea or not.
I'm somehow I didn't quite follow that. Maybe the sound wasn't good.
Me neither.
I didn't hear. I'm afraid I didn't hear. I was trying to listen, but yeah, there were kept being gaps in what I was hearing. So I'm afraid I didn't catch what you were trying to say.
Okay.
Julio, can you share your screen and show us a scheme or draw it? I don't know, like make it more visual for us, maybe.
And Kimberly, if you wanted some help with something else, Gilberto, could you join Kimberly in a breakout room and maybe see if you can help her?
Yes.
When player is crashing, it's because there's a typo in the XML. That's usually why player.
Okay.
Occasionally when you hit stop, player will crash when you try to run it again, in which case you have to relaunch it.
Okay.
I don't know why it sometimes does that, but usually if it's crashing when you start it fresh, it's a typo, it's a syntax error in the XML.
Room 1?
No, go to room 2.
No.
Okay, Julio.
Yeah, he's setting up his drawing machine.
I won't promise that I'm going to have an answer today, but I'm happy to look at it.
All right. Let me just change this there. Now I need a new page. Okay, let's try.
I'm gonna take off. Thanks, you guys. See you tomorrow.
Okay, thank you, Sharon.
Thank you.
Okay, I think I'm sharing my screen now. Okay, can you see it?
Yes.
Yes. Now this. Okay. So this is like the sample. It's a film made of material film. It's inside the particle accelerator, so the ion beam comes like here, and then it passes through the material, and in the process it creates bubbles, small bubbles with an initial radius. So what we believe is that when the ion is passing through, there's a temperature change and it's so fast that it creates like a hot cylinder, and the rest of the sample is cold, and inside is hot. So there's a probability of creating bubbles. And now what I am doing is I changed every cell fluctuant to like the double of the value. But maybe I was thinking, if I create like a very localized field that starts to spread or diffuse, maybe, and I can interact the bubble cells or the material cells with this field. I don't know like exactly how, but maybe it's a better idea to control what's happening, because for now it looks like not just like a silly model. I'm saying, oh, you create X bubbles, like 50, 10, 20 bubbles you will create with some probability. But it's like the program is doing what I'm telling him to do, and not like seeing the phenomena occurring naturally. Okay, so I don't know.
Well, so
I'm trying to what?
What's the physical mechanism here? You have the beam is depositing heat in the material, right?
Yeah, actually there is the nuclear energy loss and the electronic energy loss, and both of them creates bubbles in different ways. The one creates like the ions start passing and boom, creates a bubble, and the other one starts doing like fluctuations and oh, now I create a bubble.
But it's creating it because of heating, right?
Yeah. So a big energy loss in random points.
Okay, so but if it's at a random point, then you have to decide how you're going to represent that random interaction. And so it's not a terrible thing you can calculate, for example, you know what the profile of the beam is, and you probably know what its absorption profile is through the material. Yes. And so you can calculate what the density of the incident beam is at every point in the material. And then
yes.
I've forgotten the name of the formula, but there's some formula that tells you what's the probability, given that density, of interaction of the two kinds you have at any time. Right? What is a giant or something like that will do that kind of calculation, right? There's Monte Carlo things that'll do that. Yes. And so there'll be some probability that'll say at each time, at each position, given what the what the density, what the energy profile of the beam is, what's the probability there's an interaction that deposits a certain amount of energy at a given location? And that's what you're doing. Nice. And that's what you're doing, isn't it? You're saying at each time you roll the dice and you say at this time there's a probability of it deposits energy here, it deposits energy here, it deposits energy here, right?
Yeah. Yeah, but in a very simplified way.
Right. But that's not, I think that's not unrealistic. You have a particle that comes in, it lands somewhere, it deposits some amount of energy, and then if the energy is enough, it grows a bubble at that location.
Yeah.
And I think that's not a crazy thing to do. You could certainly put in I mean, you could calculate the profile of the beam as a field, but that profile will still only give you the probability, the local probability of nucleating a bubble, because it's not a continuous process. It really is an event where there's one ion that comes in and deposits a lot of energy.
Yes.
It's a little bit like the analogy for the things Pedro does would be with viruses. We represent the concentration of the virus as a field. but the cell either becomes infected or it doesn't. So you read the field, and then the probability of being infected depends on the field concentration. But then you have to say it either did or did not become infected. And so you have a probability of infection that depends on the concentration.
Yeah, so maybe it's an astroarc, unnecessary astroarc, maybe.
Well, I'm not saying it definitely is, but it could be. But what you want is to make sure that the profile of the beam and the probability of nucleation are correct. And that's something that a nuclear physicist needs to know is given the density of the beam, what's the probability of an interaction at a given point? And I know the radiation physicists, for example, for cancer therapy, do those kind of calculations. But of course, that's in a soft tissue with X-rays typically, or maybe proton beams. In a metal, it'll be a different result.
You're seeing my folder now?
Yes.
I can see it, but the images are pretty small. So if you click on one, and then Omar has a question.
Yes.
Yes. Are you familiar with GN4? Julio?
Wait, with what? Sorry?
GN4. It's a
GN4.
I can write it.
I don't believe so.
It's a radiation transport Monte Carlo code. And
okay, I think I need to study more. Can you write the name of it?
It's in the chat.
In the chat? Yeah.
Okay. I'll look for it.
So...
Oh no, I don't know it yet.
It's a paper that calculates that does Monte Carlo to calculate the beam profile and the probability of an event.
Yeah. Can I share my screen really quick?
Yeah,
please go ahead.
Yeah, let me just show what I have already achieved. Like, imagine this as the material, and as soon as it keeps going, I'll make it bigger. So it's like growing as expected, and the bubbles start to, be there. It takes a lot of hours, so like 26 hours to simulate this, and it's not very cool. But okay, I'll stop sharing. How do I stop sharing? How do I do that? Oh my god. How do I stop sharing?
Yeah, I'm also wondering, while Omar set it up, whether one
Did I stop sharing?
single, yes, you are.
Okay.
Whether one single decay event, energy release event, is enough to produce a bubble, or if you want multiple synchronized collisions in the same spot to reach the high enough temperatures to form a bubble there. So I believe that in your experimental apparatus, you guys are using a fairly dense beam with lots of particles, and I would imagine that they scatter inside the material. So the beam would probably diffuse inside the material, like the Galton board, and then accumulate in different regions with different densities. And probabilistically, some regions will have more density than others, density of particles, therefore have more energy release there, and maybe that's enough to accumulate heat to generate a bubble. Because I'm not sure if one single decay is enough to generate a bubble. I think it's not.
No, actually, there is it's already been studied that one single ion creates around like 14 or 20 bubbles.
Wow, that's a lot. Wow. Okay.
Yeah, and considering you have no superposition effects, like no effect of two ions, the only one,
Yeah,
if you pass it creates around 14.
Wow. Okay.
Yeah, it's
Yeah,
a lot of things.
that's a lot. But with the energies that you guys are using, or do they like use a different?
It's like 8 mega electron volts, or 16 maybe. You get like the same results with 8 and 16. It's because of there's a graph of nucleus and electron energy losses. And so they like do something like that. And they both of the effects create bubbles in the same way, approximately. But okay.
Well, let's see what Omar was going to show us.
Yeah, sure.
I think that's a fascinating problem.
Well, because a similar problem is when radiation traverses water, it dissociates water molecules and produce chemical species. So, for example, this is the core of the incident radiation that can be anything, no, like electrons or heavy ions, etc. And it leaves spores in the penumbra. So different types of radiation will leave different kind of tracks. So there's a bunch of Monte Carlo codes that can handle the radiation transport in water to as a starting point for other simulation like DNA chemical damage, etc. And for example, we use it to in combination with CC3D to simulate those distribution in cell and nucleus. And this is done by translating the dose deposition in each voxel. But I can imagine that you can do something similar. So, for example, you have the water chamber, and because sorry, and I forgot to mention this, like the probability to so water molecules are excited or ionized. So with certain probability, they can transform into chemical species. But I don't know if the bubbles you mentioned forms from a single interaction with a molecule, but maybe, and if you have a like a probability of function, maybe as a probability density based on maybe the dose distribution. So with this dose, a bubble can form and so on. You can combine these ideas, no? So like the radiation in this voxel leaves, I don't know, 3 grays, and that's enough or that is like a 50% chance to generate a bubble, and maybe that's better, or that's an idea of how to.
Yeah, because actually now I can't say what defines the material, why this material creates bubble and the other don't. So maybe with this the model can be really improved.
Yeah. And that's it.
So
how much damage does that radiation do to say stem cells or germ cells?
well, he's not using it in a biological context.
Okay.
If you were doing
yeah.
cancer radiation, then yeah, that's a great question.
Yeah.
Well, in our simulation, we calculated with a Poisson distribution in terms of the dose. So, and it creates double strand breaks in the cell nucleus. So that's like a way to associate those deposition in the nucleus with the DNA damage. So, and the mean value of the Poisson distribution, if I remember correctly, is like 25 double strand breaks per gray. I don't know if that makes sense or if I'm.
Yeah, for now it does not make sense to me, but I hope in some days it will.
Well, I don't know whether we'll solve it all tonight, but let's think about it, and then we have time. Let's talk about it more tomorrow, and with day by day we can begin to develop it. I think I understand now the question you're asking better.
Yeah,
and
sure.
So we can think about ways to do this, but I don't think it's crazy just to say that there's some probability of nucleation that's dependent on the local radiation density. That's really pretty close to the physics of what's happening, and so the existing model actually is probably closer to reality than you think.
Yeah, I agree.
Yeah, because what I'm doing now is like it's like a pool, and I'm throwing small balls in it, and I'm watching the pool level grow as the volume of the bubbles keeps getting bigger. So it's not a real simulation. It's a very simplified model, and maybe with this nucleation thing and to be really improved.
Yeah, because I think the only missing I forgot the name now. I have to look that up. Link. The missing link is associating the beam energy with the probability of nucleating, and then you have your model almost complete, maybe complete already.
Yeah, I already connected the dose of the radiation with the area of the sample and the voxels and everything, but this probability part is, yeah. I've calculated the like a medium, like a constant volume that must be added to the sample for each ion, and then I calculated a constant. It's like a constant, but it's very approximated, and it's based on observation of microscopy images. So the phenomena is not taken in account, like, But sure, thank you all for the attention for now.